Hey guys, our fourth example on Maclaurin series here, and to start, let me remind you of the Maclaurin series formula, and also remind you that this fn of 0 here means the nth derivative evaluated at 0. So remember, the 0th derivative is just a function itself, so we'll have the function evaluated at 0, and then the first derivative evaluated at 0, second derivative evaluated at 0, and so on and so forth, right? Okay, cool. All right. So now, since examples 1, 2, and 3 were e to the x, sine x, and cosine x, respectively, it appeared natural that in this example, we look at the Maclaurin series for tan x. But since tan x is equal to sine x over cosine x, it turns out that the way you find the Maclaurin series expansion for tan x is to take the Maclaurin series expansion for sine x, yes, that infinite polynomial, and to divide it by the Maclaurin series expansion for cosine x, which too is an infinite polynomial. So you get there by doing long division on an infinite polynomial divided by another infinite polynomial. Now, that sounds interesting, but it's a lot of tedious work, so I'll save it for a later example. In this video, we're going to do the Maclaurin series expansion for the function f of x equals the natural log of 1 plus x. And then that begs the question, why not do a Maclaurin series expansion for the function ln of x? Well, because for the function ln of x, the first derivative would be 1 over x, and the second derivative would be negative 1 over x squared, and so on. And if we evaluate the function at 0, we get an undefined quantity. If we evaluate the function's derivative, first derivative, at 0, it's undefined as well, and the second derivative is also undefined at 0, and so on. And so that means that there is no Maclaurin series expansion for the function ln of x. The closest thing we can have is the Maclaurin series expansion for ln of 1 plus x. And so that'll be our work for the rest of this video. And so to find the series expansion for ln of 1 plus x, we're not going to use this formula. Instead, we're going to do something more clever, which is we're going to start with the infinite geometric series, which is this. Now, we know that the infinite geometric series converges under the condition that the absolute value of x is less than 1, and it converges to this, which is 1 divided by 1 minus x. And again, it's an infinite series, right? Okay, cool. Now, we start here, and we do the following, which is replace this x here with a negative x. But then that'd mean that we replace all the x's to the right side of the equal sign with a negative x, as I've done here. Yeah? Okay, cool. Now, if you simplify that, so if we simplify this last step, then we can write this next step. So, you know, we simplify things like negative x all squared is just positive x squared, and so on. You get it. But then this gives us an idea, because now it means that we have the Maclaurin series for 1 over 1 plus x. So if we have that, we know how to get to ln of 1 plus x. We just take the antiderivative. And so you guessed it. That's what we're going to do. We're going to take the integral of both sides of this second to last equation, so as to write this, what I just showed. Yeah? Okay, cool. And so then, unsurprisingly, the integral on the left side is going to be the natural log of 1 plus x, and then term-by-term integration on the right side will give us what I have here, which is the antiderivative of 1 is x, and the antiderivative of negative x is negative x squared over 2, and so on. And so we can write this in closed form as follows. In closed form means using sigma notation. And so that's it. This concludes this video. And also, look in the closed form, we start with n equals 1, not n equals 0, as we have in the formula. But otherwise, we're done here, and the next example will be for arctan x, that is tangent inverse. Yeah? All right, cool. Keep watching.